Okay, so I'm pleased to introduce our trusty lab assistants. So Winter Chen, who's a rising junior in electrical and computer engineering, and Maddie Wilson, who's a recent graduate with bachelor's. She's going off to graduate school in the fall. So they're going. Good morning. Yes. So they're going to be leading the session on power and energy.
So as he said, my name's Winter. I'm a rising junior here in the electrical engineering department. So we're going to be talking about power and energy really quick. So energy is basically our ability to do work. You guys, we all eat. You guys had a nice breakfast, I hope. We use that energy to do actions like listen to me talk. But for most of what we do, we focus on electrical energy, of course. And what electrical energy comes from is basically from the flow of electrons. So electrons flow due to charges, built up charges, and they want to dispel so they're equally placed because they don't like being, similar charges don't like being by each other. So that movement of charges causes energy. So energy is the actual work, power is the rate of time in which that happens. So most of your household appliances are rated by power levels, so your microwaves, etc. Your electricity bill is going to be based on that as well. So power is one of the major things, but your house only consumes so much power, but your power lines have very large amounts of energy and power that if they went directly to your house would blow up. So I'm pretty sure most of you guys have those electric boxes at your house.
You check my insurance premium.
So for the way these power lines work is that we have major lines that carry most of the voltage and energy, which is most of the current, which is those electrons. And then those electrons basically get sent to your house, but of course we can't send all of them, so they use a method with transformers. So the thing about these, the reason why we can't directly connect these to your house is because there's such a high voltage, so there's such high electricity, and this is because of the power in these wires. So power lines, a lot of things about cost efficiency. So, power will be dissipated, we'll lose energy, so the most cost-effective way is to have very high voltage over these lines, which is very dangerous, but allows it to have a lower rate of transmission. So there's a lot of potential there, but the flow is not that high, which helps reduce costs. So the major thing is that we use transformers in your house, so that's going to be in those boxes you have at your home. Does Maddie want to?
Sure. So just to get an idea, have you learned the interaction between electrical fields and magnetic fields at all? So I can go over that really quick. Have you heard of the right hand rule from intro to physics? Okay. So what the right hand rule is kind of tells you the relationship between the electric fields and the magnetic fields. So I'm just going to draw it out. If you have magnets here, you have the north side of the magnet and the south pole of the magnet, and you're going to get magnetic fields that go from north to south. But if you run a wire, and these are just stationary magnetic fields, if you have a wire as well that's placed between these two magnets, and you have a current flowing through, so current, Winter's going to talk about this later, but that's represented I. So you have a current flowing this way. You take your thumb, that's going to be the direction of the current, and you take your fingers, and that's the direction of the magnetic fields, magnetic lines, and then the force on that wire is going to push the wire upwards. So your palm is the force. So your thumb is current, fingers are the magnetic fields, and then your palm is the force. So when you have a wire running through here, and you have a current going through the wire, you'll notice is going to be pushed upwards. If there's no current flowing through the wire, it's just going to be stationary. Nothing's going to interact at all. So then what happens is if you have a loop of wire, and you have the current flowing this way, if you look at this side of the wire, it's going to be pushed up. But if you look at this side of the wire, it's going to be pushed down. So you're going to get that the wire is going to start to spin, the coil. And that's the basis of a motor. So that's how you're going to turn mechanical energy or like magnetic fields into electrical energy. And then you also have generators which do the opposite. They're going to take, did I get that right? Yes, so a motor is going to turn electrical into mechanical energy, and the generator is going to do the opposite, which is turn mechanical energy into electrical energy. So this is the basis of what you're going to be building today, is the motor. And we'll explain that a little bit more later. Yeah, huh? Yes. So Winter was talking about transformers and the power grid. So going back there, if you've heard of the power grid, that's just how like natural resources such as coal, water, nuclear energy generates the power, and that is dispersed across high voltage power and transmission lines. It runs through transformers, and it ends up at your houses, at your work, at your school. It operates in like 3 different voltages: at very high voltages, where it's generated, at medium high voltages, and then at low voltages which are safe to use in your home. So this diagram, I mean, these are from your books, so you can read a little bit more about it later. Yeah. So that's the basics of power and energy. Next up, we're going to have you build motors that are going to put this principle into use or into practice. Today, we're going to be building a motor. So what you need today is a AA battery, battery clip, 2 paper clips, breadboard, some insulated magnetic copper wire. We're using 30 gauge today, and a magnet. So what you're going to start by doing is taking about a yard of your wire. It could be a little bit, like between 3 and 6 feet would be about the max you want to do. So about a yard of our wire, and we're going to make a little loop. So the battery is a good diameter for the loop that you want. So leave about 2 inches off the edge of the battery and just start winding the wire. So we're going to keep going. You want to make sure it's pretty snug against the wire, and also you want to make sure that the wire stays together. You want it a tight loop. So we're going to keep winding. All right. So our battery is wound with wire. We have about 2 inches hanging off either end. So next up, you're going to pull the wiring off the battery. Make sure that it keeps its shape. Here we go. So you have a nice loop of wire. Make sure when you're winding that you always wound in the same direction, because what we're doing here is we want uniform current. Yes. So next up, you're going to take the 2-inch ends of the wire. Oops. And you're going to loop it through, pull it out the other end, and do that maybe 2 or 3 times because we want to make sure that the loop stays in place and stays snug. So I just did 2 windings there, turn it around, using the other side, do the same thing. Wind it through about twice. All right. So after you have a nice tight loop that's self-supporting, pretty snug, you want to take a scissors or a wire stripper, and just using the edge of the scissors, which I'll just use a screwdriver right now, you're going to run the sharp end against one side removing the green insulation. So you'll notice that you can start to see the copper. So it's going to turn brown on this side. Then you're going to turn your loop around once that's done. Thank you. And you're going to remove all of the copper. So do this side, turn it, do the back, turn it, so that you're going to end up with the entire insulation removed on one side, all the way around, and the other side only having half of the insulation removed while the other half stays insulated. This is important because you want current flowing through the wire only half of the time. So as the motor rotates, only half of the time will copper be touching the paper clip. So next up, we're going to take our two paper clips and you're going to bend them into little stands for your motor. So you turn the paper clip like this, and then turn the long end and make a loop. So eventually what we're going to do is we're going to take your two paper clips, you're going to fold them up, you're going to put them into your breadboard, and you're going to tape them down to keep the paper clips in place. And then you're going to feed the loop of wire, so through each of the tiny loops. So I'm using my nail so you can kind of see how it's fed through. So you have your motor, and it's just floating around in between the two paper clips. All right. Next step is you're going to take your battery clip, put the battery in, and you're going to attach the two leads of the battery, one to one paper clips column and the other to the other paper clips column. So now that we've attached our battery with one lead going into one leg of the paper clip and going through the motor and allowing current to flow through the other lead, we're going to take our magnet, hold it close, kind of move our motor around, and you'll notice once you can get it so that both copper, like the stripped areas of the wire that are with the exposed copper, are touching the paper clip, you'll see the motor start to turn. So I'm tapping the side to keep the copper in place right now. And that's your motor.